Now that we've talked about some additional applications of that model, which again, we still haven't actually solved that thing. All we're doing is qualitative stuff right now. Because in the real world, the qualitative information you can get from a model can be so much more important than all of the crazy amount of work it can take to actually quantitatively solve the thing. And to make matters worse, in some cases, there are some equations that either cannot be quantitatively solved with like an exact answer. You would need to do some numerics to figure out what an approximate solution is, or you just don't know what the answer is yet. Right? There are equations out there, which we'll talk more about later in the semester, where there are no known exact solutions to them. And this happens, right? This happens in the real world. I mentioned in, I think, the first lecture about math modeling that there's a trade-off that happens in math modeling, in everything in life, really. There's always a give and a take, but let's restrict ourselves to math modeling for right now. In modeling, there is a big trade-off that happens. When you make assumptions that are more realistic and truer to the real world, the mathematics is going to be incredibly hard. And that is because the real world is incredibly complicated, right? So in order to make the math a little easier, you have to make some idealized kinds of assumptions. And the trade-off, which we've already seen in action, is that when you make some idealized assumptions and you make the math easier, you end up having to be very careful about how you actually implement and understand and synthesize and analyze your model. Right? With the population example, when k was positive, that population is going to infinity. And that certainly doesn't make sense. Not for bunnies, not for anything, right? That doesn't make sense for a population to shoot off to infinity. However, we saw that if you take the right precautions, like understanding that on a relatively short time scale, that qualitative model can actually be pretty darn close to what happens in the laboratory setting, right? And the laboratory setting is important there because it sort of closely matches these idealized conditions that we said were necessary for our model to be applicable, right? So, and again, I talked a little bit at the end of the last video about this relatively short timescale thing being important. For bacteria, it's on the scale of hours. For money in a bank account, it could be on the scale of years or decades. For xenon, it's on the order of 1 trillion times the age of the universe, which is just mind-blowing. So this relatively short time scale is important to this qualitative analysis. But the really cool thing I find about qualitative analysis is that you can look at one model and you can get the qualitative information you need out of it, and then you can look at this wide array of different applications and you can say to yourself, as long as I'm careful about how I implement this, I know that I can implement this model to address all of these different situations. I think that's really interesting and incredibly beautiful that you can take this one very simple model, which was not too hard to wrap our heads around so far, and it has great applications that are extremely ubiquitous. They're all over the place. In finance, chemistry, physics, biology, they're everywhere. All right, so the one thing I want to do now is discuss how we can possibly improve this. Right, we saw the shortcomings of the original model, and let me just write it here so we have it in front of us. Right, our original model was that our population changes proportionally. That's supposed to be a K. Apologize, my hands are cold. P prime is equal to KP, right? So your population grows proportionally to how many things are currently in the population. And our other assumption was that you can walk outside and count the bunnies initially. Or, if it's a bacterium in a petri dish, maybe the mass of the sample of bacteria, and on average how many bacteria there will be per, square millimeter or square centimeter of the petri dish, etc., 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 you can walk outside and count your bunnies, right? Long story short. So, I asked you all to submit some ways that you thought we could improve this model for one of your homework assignments last week. And here's just a few of your ideas. You gave some great ones. I just wanted to point out a few of them. And some of them could be sort of condensed into these. So if you didn't say these verbatim, then there's a good chance that I'm going to include yours just as a subset of one of these. All right. So the three that really jumped out at me were adding a food and water supply, adding predators or competition, right, non-violent competition for resources, and adding in a male-female ratio that's not necessarily 1-to-1, like how I sort of imagined this would happen, right? I sort of imagined that to make our lives easier, our population would always be 50-50, right? It would always be half male, half female. Now, I love these ideas. Let me briefly discuss them. All right, say we want to add a food or a water supply. Let's call F our food supply. Well, F is itself going to be a population. And now, you might think to yourself, and some people did put this in their notes when I asked for this submission, some people did point out that water is going to be significantly different than food. The reason being that water doesn't have a gestational period, it doesn't have a reproductive cycle, things like that. It's not as seasonally affected depending on what climate you're in, things like that. All right, so that is true. However, it is still a population that is affected by a sort of reproductive cycle. If you think about what the reproductive cycle of water might be, it is the water cycle, right? This is how a population of water would be considered to be reproducing, decaying, growing, however you want to think about it, in the wild. All right, water is also much more complicated just for a variety of reasons that, frankly, I don't want to get into right now. It can be extremely complicated to try and model a water supply. If you're looking at something like a lake or a pond that has been there for thousands of years or millions of years, possibly hundreds of thousands of years more likely, then, you know, it's a little bit easier to say what's going to happen. So yes and no. All right, that's my answer to this one. Water is still a kind of population that you would have to account for. It is still dynamic, right? It can still change. So food and water, you're still talking about modeling another population. So at the very basic foundation of it, you would have to start off with some kind of model of the food population itself. All right, it changes with time. Now, ditto for predators and competition, right? If your predator population, I'm going to call it F again. F instead of being food, F is going to be foxes now. F is still a population that you will have to model. All right, for competition, maybe you're talking about squirrels, right? If the squirrels are competing with the bunnies for their food, this is still another population that you have to model. Now, here's, I think, maybe the subtlest of the points. The male-female ratio in your population. All right, so the male-female subsets of your bunny population. Well, if you think about what your bunny population is, it can be viewed, if P is your bunny population, it can be viewed as the male plus the female populations within your bunny population. In other words, the males and the females are each their own individual populations. And there is a theme that's going on here with all three of these bullet points. And that is that in order to add any one of these three new factors to try and make our model more realistic to an actual wild bunny population, we're going to have to be able to model a second population. Whether it's the carrots, or the water supply, or the foxes, or the squirrels, or even just looking within the bunnies themselves and looking at the male population as acting separately from the female population, growing and changing separately from the females. In each one of these cases, we're going to have to be able to model a second population. And if that were the case, right, if we were just modeling like two populations that existed side by side but had nothing to do with each other, well, we know how to get our foot in the door there because we know how to start modeling populations. It's doing the exact same thing we just did. However, what makes all three of these really hard is that you're not just modeling two side-by-side, totally non-interactive populations. You're modeling heavily interactive populations, right? The carrots are being eaten by the bunnies. And possibly the reproduction of the carrots might rely on the bunnies themselves, right? If the bunnies are eating some carrot seeds, and then they hop away a mile and they poop out the carrot seeds, then you're going to get a new carrot patch in a different place, right? So the reproductive cycle of the carrots may be heavily dependent on the bunnies themselves. And of course, the bunnies are dependent on the carrots. Same thing is true for the foxes, right? Foxes are heavily dependent on bunnies. The bunnies are going to be heavily dependent on the foxes in the sense that if there are a lot of foxes, the bunnies are in trouble. If there aren't as many, then the bunnies are more free to have their population grow. Ditto for the squirrels, right? Same exact logic, just without direct violent competition. And the males and females, they very much are interacting within this population, right? So in each one of these three cases, I think the word that I'm trying to get at here is, number one, they're dynamic. All three of these are dynamic, and they're dynamic interactions. Oops. All right, so we have dynamic interaction between all of these things and the population that we, at the start of the day and at the end of the day, are supposed to care about, which is the bunnies. All right, so all three of these are going to be complicated, right? They're all going to involve a second variable, okay? So whether it's the food, the foxes, the squirrels, or male versus female, you're talking about taking your one variable bunny situation and incorporating a second variable. All right, so the jump that we're talking about here is akin to going from Calc 1 to Calc 3. All right, you're skipping a whole lot of material there. So that's going to be tough. All right, and we will get there, but not today. Okay, so the thing that I want to add to our model is something which we can hypothetically take to not be variable. All right, it's something that we should be able to take to be constant, or at least relatively constant. Again, if you start talking about short-term versus long-term kind of ideas of our model only applying in the short term and things like that, I want to look at something and add something to our model that will be relatively constant. Okay? And this is one of the factors that was in our original big list that you guys helped me compile of factors that might impact a bunny population in the wild. All right, so the factor that I want to add on that's going to be relatively constant in the short term is going to be what's called a carrying capacity. All right, and this is, I'll denote it by K. And this is just the number of bunnies that the environment that they live in can possibly support. All right, it's the maximum number that the environment can possibly support. All right, so I think the example I gave in that video last week was, say your bunnies need to live in the forest. Well, if the grove of woods that you're looking at is only so many acres, well, there are only physically so many bunnies that could fit within that acreage of woods. All right, so this is the kind of thing that I mean when I say a carrying capacity. And we'll refer to it by the letter K. All right, so we need to think about in what way we can create a model that includes this maximum number of bunnies that can live in the environment at any given time. And I mentioned that this idea of math modeling very much is like a staircase that you're building as you go. All right? You don't start from scratch every time you want to do something with a model. You always try to use what you've already done and build upon it and try to improve it. So let's start with our sort of fundamental model, right? Our first model, which only incorporated two things, right? It only incorporated the fact that we can try to understand their growth rate, right? How fast are they on average being born, and a net growth rate, so being born versus dying, or dying versus being born. And the other thing that we assumed about this population was that we could walk outside and count them. Or, like Professor Sterrett in the bio department trying to use drones to count turtles, right? So something like this, right? Hypothetically, we can walk outside and count them. So this is our first model. And what I want to do now is just try to think about what a population's going to do if it only has so much room to grow. Right? A very good way to think about this might be like bacteria in a petri dish, right? You put a food supply in a petri dish and you introduce a bacteria population, and they're going to eat up the food supply, assuming you give them plenty of food. They're going to eat up this food supply, and they're going to subdivide, and they're going to reproduce, and the bacteria population is going to expand. They physically only have the few square inches of the petri dish to expand into. They will eventually literally hit the boundary, they'll hit the edge of the petri dish, and they'll be unable to expand anymore. Okay, so what I want you to think about is how this rate of change, P prime, how do you think this should be affected by the carrying capacity? All right, so what I want you to think about is what might happen to P prime as P approaches K. Right? As your population gets really close to the carrying capacity, what do you think might happen to P prime? All right, I'm not asking what's going to happen in the model I have written right here, because we're trying to change this model. Right? There is no carrying capacity in the model I just wrote. I want you to think, just, forget about what we already said about how this model is going to behave. Just think about a population like a bacteria in a petri dish. What do you think that population is going to do as the population approaches the carrying capacity? Right? How is that population going to react and behave to that? So take a minute, pause the video. I want you to take a little while with this. Set yourself, let's say, a 4-minute timer, all right? And I want you to think about what this population is going to do as it gets closer and closer to the carrying capacity. Just jot down a few notes about how you think it'll behave. It doesn't have to be mathematical in nature. Could just be, sentences. But write down a little blurb about what you think this population should do, and then try to relate that back to how P prime might have to behave. All right, so take a few minutes, maybe 4 minutes, set a timer, and then come back and resume. All right, so, we've already seen these examples. I just didn't mention what was going on past the first little bit of time. All right, this is what I kept referring back to in the last video as this like relative time scale being important. So what I want to do now, instead of looking at the initial time, right? The initial time was important for us before because it sort of fit initially that qualitative sketch of how our population should behave. What I want to do instead now is look at these other parts, right? Let's look at the other parts of these graphs that didn't necessarily fit our initial population model, right? This is where things started to fall apart for us. And let's look at these instead. All right. So what is going on here? And again, the lines that are included in this graph, these two starred graphs, the actual curves that are in there are best fit curves. It's the circles, the open circles in the bottom one, and the black squares in the top left one. Those are the actual data points for these populations of bacteria that were measured. And the top right one is the deer that were put on this island. And you can see the same kind of, heuristically speaking, the same kind of behavior is going on. The deer have something more interesting happening where they actually got a spike, right? They spiked first, and then they sort of petered out. But you still do see the same qualitative kind of behavior, right? You see growth for a little while, and then it starts to flatten out, right? And the same thing is true in all of these cases, right? You see growth, and then it flattens out. And the bacteria examples, which are the top left and the bottom, these I think are the most interesting because these are the ones that are physically constrained by being inside of petri dishes. And so what you can see is happening here is that by, let's say 8 hours, I'm looking at the top left one here, right? By 8 hours, this population's growth has pretty much slowed almost to a halt, right? They are really slowing down in terms of their growth rate. And physically speaking, you can sort of imagine how this population would be growing out toward the boundary of their petri dish, right? They're literally hitting the boundary of their environment. And their reproductive rate is slowing because of that, right? They're not reproducing because they don't physically have room. Same thing is true down here. This one happens, around, I would say the downturn begins around maybe 6 hours, right? So just a tiny bit earlier than the other one. And for this deer population, this one's a little trickier because of that spike, but the same kind of qualitative behavior starts somewhere around maybe year 4. All right? And now this deer population has that really interesting spike before it peters out and sort of levels at around 80 deer. It's got that really interesting spike, and that's because the deer don't live in a petri dish, right? They live in an island. And so what actually happened here, and you can see it in the graph, is that they actually reproduced beyond their environment's carrying capacity. And nature, being the amoral thing that it is, it corrected that mistake, right? And so the deer population died down to the actual carrying capacity. So in the real world, it is possible for populations to exceed the carrying capacity, and then nature will do the adjustment for them, right? They will die down, and their population will normalize to the carrying capacity. All right, so heuristically speaking, meaning I'm not saying anything really exact here, just sort of gut feeling, intuitively speaking, the same thing is true for all 3 of these cases, and that is that as a population approaches its carrying capacity, its growth rate should slow down. Right, that's what we're seeing here. All right, so let's write this all down. All right, as P approaches K, the carrying capacity, P should slow down. Right, that's just exactly what I said verbatim. Now, what we need to do is put that into some calculus language. This means that P prime should do something. All right, so what does it mean for P to be slowing down? This means that P prime should be doing something. If you look at the graphs, right, it looks like our functions are leveling out, right? It looks like our data is leveling out. So to fill in this box that I've drawn down here, right, to fill in the blank, what does a derivative look like for a function that should be leveling out? All right, so I want you to pause the video, take a minute, think about what should go in this box here. Where should p prime go so that our function levels out? All right, hopefully you came up with the same thing I did. Our function leveling out means that it's looking more and more like a constant. Constant functions have derivative 0. So what we should be able to say here is that p prime should go to 0. All right, so in terms of adapting our original model to reflect this situation, what we want to do is take this first line here, which involves p prime. So what we're doing is we're saying that under ideal conditions, it will grow proportionally to its current population. And now we just want to introduce something into this line that will account for this fact here, that as p approaches k, p prime should approach 0. Right? We want to introduce this fact somehow mathematically. And there's, well, why don't you take a second, right? Pause the video, take a minute, think about what you could do to this line right here. I said 1 minute. Let's make it 5. Set a 5-minute timer. All right? Take a little while and try to chew on this. What can you do to this line that will make it, right? What can you introduce into this line that will make it so that as p approaches the carrying capacity, p prime approaches 0? There's more than one way to do this, all right? So take 5 minutes, take a good chunk of time, and try to write some things down. Experiment a little. It's good to make mistakes. All right, see if you can come up with a way to mathematically make it so that as p approaches k, p prime approaches 0. After 5 minutes, come back. Okay, so regardless of what you've got in front of you, there is probably, I have a hard time with this, calling anything the simplest way to do something, because simple is so incredibly subjective, but there is a simple way to do this, which is to, hang on, go the other way around, which is to see how far your population is from the carrying capacity. And if you want p prime to be going to 0 as p gets really close to k, well, what that's saying is that as p gets close to k, right, as p goes to k, p minus k, or sorry, k minus p, will go to 0. And that will make p prime go to 0. All right, so multiplying by this, this new term, this new factor, I should say, does exactly what we need it to do. Now, I put p minus k first. That would have technically been fine, because that arbitrary constant k in front of here would have absorbed that extra minus sign and made everything just fine. I want k minus p instead, because I want to imagine that p should be less than the carrying capacity in general, right? We generally want to assume that our population is less than the carrying capacity. And that will make k minus p a positive quantity. All right, so we want the growth or death of our population to be largely, almost entirely influenced by the sign of k, not necessarily by the sign of other things that we've included in our model. So, right, so this is really just sort of a little technical point. That's why I did k minus p instead of p minus k. Either one works. Okay, so what I want to do now, really what I want you guys to do now, is to sketch the phase plane for this thing. It is going to be more complicated, more interesting than the last phase plane. All right, so the exercise here. All right, so I want you to sketch the phase plane portrait of this thing and discuss the fixed points, or where are they, what do they actually mean, and discuss the asymptotics. All right, the asymptotics are going to be broken into a few different cases depending on whether you are above or below the carrying capacity. All right, so there's a good amount of work to be done in here. But the basic idea is the exact same kind of analysis that we did before, involving finding the fixed points, figuring out where p prime is positive or negative, and identifying directions of flow from that.